Hi, in this video again we are going to talk about the AVL trees, so let's get started. We have been talking about what's the problem with binary search trees and what's the motivation behind keeping a binary tree as balanced as possible. So the running time of a binary search tree operations depends on the height of the binary search tree. So we should keep the tree balanced in order to get the best performance. And that's why AVL trees came to be. It was invented in 1972 by two Russian computer scientists. In an AVL tree, the heights of the two child subtrees of any node differ by at most one. So we have a left subtree and a right subtree for every node, and basically the difference between the heights of these subtrees cannot differ more than one. Okay, another solution to the problem is the so-called red-black trees. AVL trees are faster than red-black trees because they are more rigidly balanced, but needs more work. So that's why it is a bit slower as far as constructing the AVL tree is concerned. Operating systems relies heavily on these data structures, but I think that in the 21st century, red-black trees outperforms AVL trees because they are not rigidly balanced, and that's why constructing a red-black tree is not going to take so long. It's very important that most of the operations are the same as we have seen for binary search trees. Every node can have at most two children. The left child is smaller and the right child is greater than the parent node. So basically, this is the typical binary search tree feature. So it's going to be the same. The insertion operation is the same, but on every insertion we have to check whether the tree is unbalanced or not. Okay, what do we have to do? We just have to decide whether the left and the right subtree's height is going to differ by more than one or not. And according to this information we have to make the rotations. Okay, the deletion operation is the same, and the maximum and minimum finding operations are the same as well. So basically it's very important that a balanced binary tree, for example an AVL tree, is just the same as the standard binary search tree, but on every insertion we have to check whether the tree is balanced. And if it's not balanced according to the height parameters, then we have to make these rotations in order to make it balanced again. So let's suppose that we have this tree-like structure. Okay, we would like to find the 30. We start at the root node again. This operation is just the same as we have discussed for binary search trees. 30 is greater than the root node, we go to the right. 30 is smaller than 40, we go to the left. And this is the item we are looking for. So that's all about the search operation. It is the same as we have discussed for binary search trees. What about the minimum finding? We start at the root node, and we know for certain that in a binary search tree or a balanced binary search tree, doesn't matter, the right subtree is going to be greater and the left subtree is going to be smaller than the given node. So if we are looking for the minimum item, we have to go to the left as far as possible. What does it mean? It means that as far as we bump into a null pointer, we go to the left. It has a left child, so it's not a null, we go there. 8 has a left child 5, so we go there. But the 5 doesn't have any left child, so it's going to be the minimum item we are looking for. What about the maximum item? We know for certain that first of all we have to start with the root node, and the right subtree is always greater than the given node. So if we would like to find the maximum item, we have to go to the right as far as possible. Okay, the 40 has a right child, so we go there. But the 50 doesn't have any right child, so it's going to be the greatest item in this tree. So just to summarize again, we have been talking about binary search trees. We have been discussing several operations such as insertion, deletion, and the search operation. The average case running time is going to be logarithmic, but the worst case running time is going to be linear for binary search trees. That's what we have been discussing in the previous video, that we may end up with a linked list, and insertion, deletion, and search operation is going to take linear time complexity in a linked list. It is slower than the logarithmic time complexity. What about the balanced binary trees? We came to the conclusion that the worst case running time is going to be equal to the average case running time. So the logarithmic running time is going to be guaranteed, and this balanced binary tree is going to be very, very predictable as far as the running times are concerned, and it is very, very good features for AVL trees and red-black trees. Thanks for watching.